Okay, so good morning, everyone. Thanks for coming this early. And today we're going to talk about redundancy driven development. This talk will be focused on how we can use some common techniques on carefully introducing new behaviors in our code bases. And what I mean by that is, rewriting or refactoring parts of our code base. And we're going to talk about today how we can address these rewrites or refactors without wreaking havoc on the whole code base itself and on our apps as a result. So first of all, let's do a quick introduction. I'm Fabian Shallari. I'm based here in Berlin. I was born like a short hour drive from this place. You can take a guess now and ask me where this is in the QA in the end. So for those of you who will fall asleep during the talk, make yourselves comfortable, but make sure to wake up for the reveal during the Q&A. I've been doing Android since 4.4 KitKat, so I was literally super excited about the new animations in Lollipop when that came out. I'm a mobile engineer at SoftUp Technologies GmbH, which is a software development agency based in Munich, and working there actually gives me the opportunity to work with different products and different teams. So this talk is actually inspired by two different projects which I worked at, and one of them was at EmoScout, and one of them was at Payback, which is actually the team that I'm currently working with. So despite these two projects being quite different and being at two different companies, I noticed quite a lot of similarities between the techniques and patterns that kind of naturally emerged while working at both of them. So today, a quick overview of the agenda. We're going to start about actually talking about the definition of redundancy. Then we're going to take a look at some redundant components in software engineering, how we can apply this redundancy during this transition or rewrite or refactoring phases, and then we're going to look at how we can adapt our code bases, adapt as a team, and then clean up in the end. All right, so redundancy. I actually had a really hard time coming up with a good term on what to call the common techniques and patterns that we're going to talk about today. So I asked ChatGPT, it failed to give me a proper name, and then after thinking about it, the only suitable umbrella term for what I'm going to talk about was this strange English word, redundancy. So if we look at the definition of redundancy in the Oxford English Dictionary, it says, the state of being or no longer needed or useful. So judging from that, it is quite odd that I would choose this kind of term. So what is this talk even about, you might wonder. Well, as it turns out, English, unlike German, for example, is a very flexible language, and words actually have different meanings depending on the context that you use them. So in engineering, redundancy means the inclusion of extra components which are not strictly necessary to functioning in case of failure in other components. So in layman terms, that means there is extra stuff in a software system which is there in case your main stuff fails to work. Going a bit beyond that, in this talk, what we are going to mean about redundancy is going to be the inclusion of extra components which are not strictly necessary to functioning. And that is quite similar to the previous definition. So basically, it means that there is extra stuff in a system which plays no main role in what the system is supposed to do, but that extra stuff is there, so it ensures that the main stuff that you put in the system works properly. All right, so to try to actually convince you that all this redundancy stuff I'm talking about is not something I made up when I bumped my head in some place, we are going to talk about one of the most important and greatest events to happen in modern history. I mean the moon landing. So let's take a look at the first moon landing. This is the Apollo guidance computer. During the actual moon landing, the lunar spaceship had this computer which was responsible for guiding the lunar module, among other things, to land on the moon. The Apollo Guidance Computer, or AGC for short, is pictured here, was custom built at MIT by a team of about 1,000 people. And the software in this computer was actually really complex. And it was responsible for guiding the ship during the whole lunar landing, doing complex guidance, algorithm calculations, calculating the trajectory of the ship, actually firing the motors so it steered the ship to actually land in the landing spot. And it actually had a subroutine or a program which could land the ship automatically on autopilot, even though that didn't getting used in the end. So the Apollo Guidance Computer responsible for a lot of complex compute-intensive tasks. And why is this interesting? Well, it turns out that the software had this very complex and difficult task and some very interesting restrictions which resulted in some very specific design decisions. Well, first of all, this is 1969, so CPUs have a clock speed of 1 megahertz, and the computer could run only 7 concurrent jobs at most. So imagine having today a computer whose software could run only 7 Kotlin coroutines. And you're about to land on the moon, so good luck with that. This computer actually checkpoints good state, which means that every now and then the position of the ship, the speed, and other data from the ship would get saved in memory. And that was pretty useful because the computer would soft restart on executive overflow, meaning that if the CPU was overloaded, it would shut down the software, and then the software would restart. And it stopped restarting and stopping and restarting and stopping, so it didn't get in a loop because it had this thing called a priority job scheduler. And actually, this job scheduler made sure that whenever the computer restarted, it would restart only the jobs which were deemed of utmost importance. So trajectory calculations was a very important job, so it would restart that. Sending that data back to Earth, so the team of people working on Earth on the mission would look at the data, debug the computer in real time, and in case there was something wrong, they would say, let's go on with the mission or let's abort the mission. And that is important because on the silver device, which is an I/O device there, astronauts would frequently schedule jobs or tasks which were deemed not so important. So, for example, there was a task which would calculate the difference between the ship and the moon in 2 different ways, and it would display the difference between these 2 different ways of calculating it at the silver device all the time. So whenever, for example, you had an executive overflow, the priority job scheduler would then restart the jobs that were deemed important, but not the jobs that were deemed not so important. All right, so you are on the moon. You have a computer which runs 7 jobs at max, and it checkpoints every now and then the good state. It restarts if the CPU overclocks, and it only restarts the highest priority jobs. And that was actually pretty useful because during the whole lunar landing, from takeoff until actually the 2 astronauts were about to land on the moon, the computer worked perfectly. It gave no errors, but then it gave 5 program alarms just as the lunar module was about to land. And at first thought, the astronauts thought, well, there's something wrong with the computer. It's giving these program alarms just as we were about to land. But it actually turned out that the computer worked perfectly during the whole mission. And it was actually a hardware bug which caused all the 5 alarms. And the priority job scheduler would come into place, and then it would restart only the jobs that were important. So it managed to land people on the moon. So this guidance computer had actually redundancy built into itself. And all these properties of this computer are what we would call a redundant system today. So in order for the AGC to work properly, to actually calculate the trajectory, it doesn't need a job scheduler or doesn't need to checkpoint good state. It just needs to calculate the trajectory. And this pioneering work was made by this amazing lady called Margaret Hamilton, and she led the team at MIT who worked on this computer. And she was actually one of the first people who worked on software who applied what we call good engineering principles during her work, testing, redundancy, fault tolerance, which also gave the rise to the software engineering field as we know it today. So at her time, people working on hardware were actually called engineers, while people working on software, they were just some programmers, I don't know, doing some weird stuff. And this is important because we kind of see the same thing happening today. So there are people claiming that programmers shouldn't call themselves engineers. You can run a company with 10% of the staff and something like that. And I imagine Margaret would not be so happy about that. And just keep in mind that this has been, this pushback has been there since the beginning of time when Margaret was working on this computer. And when she claimed that people working on software were software engineers, people laughed in her face and stuff like that. So, all right, so far we have talked about redundancy, what it means for our field, and the fact that redundancy has been part of our disciplines since when it was first formalized as software engineering. So let's come back today and consider a more modern context. What are some redundant components that we can leverage today in order to achieve a satisfying degree of redundancy for our systems and apps and make them more reliable? Well, the first two of them are actually quite obvious, I think. Tests. So I hope we all write unit tests regularly, and our QA teams test apps on each release. So just as the Apollo lunar mission simulated the landing hundreds of times on Earth, we also write tests today to simulate user behavior for each release. So nothing has changed, pretty much. The next thing is crash and performance analytics. So I'm sure we all send Firebase Crashlytics data or Bugsnag Crashlytics data to some server. Whenever something goes wrong, we look at the data, and then we do something to fix our apps. And this is just what the Apollo mission was doing. The computer, one of the computer's main jobs, which would get restarted and the rerun on every executive overflow, was it would send data back to Houston so that they could analyze and act accordingly. And there are four other things that I want to talk about today. And in order to do that, let's look at some concrete examples. So the first thing is rewriting the app initializers at payback. So I'm sure that most of our apps have something like this. So an app initializer, which when the app is created, it initializes a list of components which are critical for our app to run. And yeah. When I joined Payback, this is what it actually looked like. And it's not that bad, but there are a bunch of things which can be improved here. First, in the constructor, there's a duplication between the constructor and the init method, so you are kind of declaring what you need in two places. And in the init method, there's something which is not so obvious, which is that order matters, right? So here, the work manager needs to initialize after the crash report, and the crash report needs to initialize after the analytics, and so on and so forth. And basically, this is kind of an implicit order in the init method. And to make this order more explicit and simplify how our app initializer works, we ended up rewriting it. And this is how it looked after the rewrite. So we get a set of initializers in whatever order in the constructor, and then we sort them with a special extension method, and then in a for each loop, we just initialize each one of them. And how we do this is quite cool, actually. We generate some code with KSP, And the code we generate is kind of beyond the purposes of this talk, but this is what gets configured, actually. So it's just a comparator interface with a sort order annotation, and the elements in the sort order, you can see that they're explicitly, it says sort order, so the order is important. And from this interface, we generate that extension method. So this is what we started with, and this is what we ended up with. So in order to go from this one to this one, we can just replace the old implementation with a new one and call it a day. But when you have 10 million users in your app, it's not that easy to do. So in case you make a mistake, or some of these initializers have any undefined behavior, which was not obvious in the first implementation, you take quite a big risk if you just replace one with the other. And one of the risks you take is crashing your app during initialization, which is actually not that bad, since these scenarios usually are catched early during testing. An even bigger risk is introducing data inconsistencies. So maybe you have some initializer which takes care of some encryption, and then you end up with corrupted data, which doesn't make sense, and the app crashes then only on some more deep flows inside your app. And a third risk is actually introducing too much complexity all at once. So the initializer rewrite will probably not be the only thing which is pushed in one release, and therefore you are kind of multiplying the complexity for your QA team by introducing another change in that release. So everything which was planned for the release kind of gets a multiplied complexity by just pushing these app initializers. So how do we go about in introducing this change? If we take a step back and visualize it in the diagram, here we start with what we had in the beginning. And the first thing that we do is actually we extract an interface from the app initializer, and then we rename the existing implementation into legacy. And this way we are also kind of signaling to our colleagues that this is something which will soon be removed. After that, we introduce a delegator class in front, and then we write the new implementation. And then actually the delegator is useful in order to switch between the old implementation and the new implementation. So what we want to achieve is that we want to rewrite a specific component in our system. And in order to minimize risk, we need to do a gradual transition to the new component. We can just flip a switch and go from the old one to the new one. So the way that we actually do this transition is by doing this kind of interface delegation and new implementation pattern. So we can tell our QA team this is a new feature switch which you can turn on and off so that you can create a more isolated test environment. The feature switch can also be off in production and on in debug, while our QA team tests several regressions across different versions, and we get the necessary confidence to turn the switch on in production later. Another advantage is that we can control the feature switch remotely, meaning that once we have tested it enough, we have built the right confidence that it's working, we can turn it on in production, monitor our crash data, and if something goes horribly wrong, we can always turn it off later. So how does this connect with redundancy? Well, let's imagine that our feature switch is off, and we are using the legacy implementation. As you can see here, all these components are all redundant components. So in order for the app to call the initializers, we actually don't need an interface or a delegator. We just need to go to the legacy implementation. And the same thing happens if we turn the switch on and we use the new implementation. Now these components are redundant. So we just need the app and the app initializer new implementation class. We don't need this interface and delegation. So let's take a look at how this actually looks in code. So for the app class that we had in the beginning, nothing changes besides the fact that this is now an interface. And the legacy implementation is renamed and made an implementation of this interface. The new implementation just needs to implement the same interface. And the delegator also implements the same interface, and on the init method, it looks at the feature switch. If it's on, it delegates it to the new implementation, and if it's off, it delegates to the legacy implementation. All right, so to do a quick summary, we are trying to transition a specific part of our app, in this case, the app initializers, from one implementation to another. And in order for us to reduce the risk that this change brings, we introduce some redundancy in the system. And the way we do that is by creating a substitutable type hierarchy, which is just a fancy name for an implementation and a delegate. And that type hierarchy enables us to isolate the parts that we want to rewrite without affecting the other parts of the app. And we put a delegator at the root of the hierarchy, which switches between the legacy implementation and the new one. So substitutable type hierarchies and delegates with feature toggles are some kind of redundancy that you can introduce into your systems to make them a bit more reliable. So basically, isolation and delegation switching. Cool. So we looked at a relatively simple example. So let's look at a more complex one. At ImmoScout, we had this problem of migrating all 10 million users of the system to a new authentication system. And it was a project which had a lot of challenges, and it was done in a time frame of several months. So I think it makes sense to look at an overview of what the project details are in order to understand kind of the complexity behind it. So basically, the project goal was to migrate close to 10 million users to a new authentication system. Some of the challenges were, all users needed to re-authenticate because both these authentication systems had incompatible tokens. So a user's identity couldn't be verified automatically by them just being logged in with a legacy system. So they had to re-authenticate with a new system as well. Migration is done gradually over 3 months. So during this time, both systems are online, and users can still use both of them. And the legacy system goes offline after the migration period ends. So due to these challenges, when we designed the new authentication system, we took a very similar design choices to what we talked about the app initializers rewrite. So the legacy and the new implementation of the auth-related code had to be in the same place at the same time. Because, not just for redundancy's sake, but because both these systems were still operating at the same time in the backend as well. Since the authentication state, is saved locally on a device, you can just flip a switch, look at the feature toggle, and then enable the new system and, log the user out. You actually have to keep the user state in a state machine, which keeps track of where the user is during this migration state. And the feature switch needs to check the state machine as well as the remote flag before it actually switches the users to the new system. And we sync migration state at different checkpoints. So when the app starts, when the user logs in, when the user makes a network request, when they log out, we sync the migration state, so we keep the users at the latest state. And what's actually really important is that the state machine needs to travel both ways. So it needs to take users from the legacy system to the new system. And if something goes wrong, we should encode the logic to take the users back from the new system to the legacy system. So if we take a look at a diagram of a simplified version of our auth system, and a very idealized one, we can create an idea of what we're actually talking about. So starting on the left, you have the client code, and these are the components of your app which do various auth-related stuff. Your usual suspects, you have OKHTTP authenticator, OKHTTP interceptor, your login screen, your logout screen. And usually, what we found out at ImmoScout was that in an auth system, you actually have 4 main interaction points. So you have 4 interactors or use cases. The first one is checking the auth state to determine whether the user is logged in or not, what is the state of the user's token. Second one is just making sure the user logs in, and the third one is refreshing expired tokens, and the fourth one is logging the users out. So all of these interaction points use a combination of a local token repository, which is like a database which keeps track of the user's token, and the remote auth service, which might be your retrofit APIs in communicating with the authentication server. So depending on how your auth architecture is designed, this is kind of an architecture of that, so a representation of that architecture rather. So how do we prepare for the migration? Well, as always, we start with isolating the bits of code, which will have to differentiate between the legacy and the new system, and we introduce an interface and a delegator for each of one. So the remote auth service now becomes an interface, it has a delegator, and the delegator can switch between the legacy one and the new one. So you have two retrofit interfaces, which one talks with the old server, the other one talks with the new server. We do the same thing for the local token repository. So we have a delegator which can save and introspect the tokens of the old system and save and introspect the tokens of the new system. So interface and delegation here as well. So most importantly, let's see how we actually go forwards and backwards in the state machine. So the delegators have to both check the same thing, right? So asking the local token delegator or the remote auth service delegator, it would need to give you the same answer, basically, whether the user is in the legacy state or in the new state. So it makes sense that they have a single source of truth. And in order for us to have a single source of truth, we save that migration state somewhere, and we use an interactor to access that state. And this is kind of what it looks like in more detail. I don't think it makes much sense to go through the whole diagram. Basically, all the things on the right of the local token and the remote auth service delegator is what you would say is a state machine. And that state machine makes sure that whenever both the local token repository and the remote auth service delegator ask the get auth migration state interactor, it makes sure that user is in a consistent state and the state is checkpointed and saved. So the way we keep track of all this, we did a sync event on each of the events which are of interest to the state machine. So on app start, on login, on a network request, on a logout, we would check the current token, the feature toggle, and the auth state syncer, which is actually our state machine, would then save what it thought that the user was in that state. So how do we travel in the state machine from the legacy system to the new system and backwards? Well, on the first sync event, if the user is still using the legacy token and the feature toggle is off, the user is still on the legacy auth system. And this is what the delegators will actually see. So let's say that we turn the feature on and user has still a legacy token. The state machine would still be on the legacy system. So it would not migrate the users immediately because it needs to check whether the legacy token has been invalidated yet or not. And, to make sure that, this migration is done carefully and everything goes all right, you can turn the feature toggle 5% on, wait for some users to eventually go to the new system, look at the data, and then increase that accordingly. So if the user gets logged out on a logout event, logs out by themselves, or we invalidate their token remotely, and the feature toggle is now on, this is the first, actually the first time that the state machine says we are ready to use the new authentication server. And on the login, users will have a new token, and we are now using the new auth system. And if nothing changes on each subsequent network request, we still use the new implementation. And now, let's say that we decide to go back and we turn the switch off. Users will still use the new system as long as their tokens are still active. So same principle here. It doesn't really matter if the feature toggle is on or off, as long as the user's token is still valid. However, if we try to, if something goes horribly wrong with the new auth server, and we decide to invalidate the user's token because something went wrong. When the feature toggle is off and the user is logged out, this is where the first time they're marked that they can go back to using the legacy system. So two things need to happen. On the next login, they have their legacy token again. And we can fix, during this time, whatever was wrong with the new authentication server, and the cycle can begin anew. So basically, all this mambo jumbo means that you need to have a two-way state machine. So the state machine needs to go from the legacy system to the new system, and from the new system to the legacy system in case something goes wrong somewhere. All right, so to sum things up, how does this tie up with redundancy after all? We are trying to transition all these 10 million users from a legacy auth system to a new auth system. And in order for us to reduce the risk that this change brings, we introduce some redundancy in the system. So the way we do that is with the two, So with the 2 points down there, stage rollouts, if you remember, you can actually increase the feature toggle to only 5% of your users. You monitor the data, you build more confidence, and you increase or decrease on how things go. And the state machine will take care of reverting the users back or going forwards to using the new system. So just as the Apollo guided computer, it would checkpoint good state, and it would restart from the last good state. We do here a similar thing. So on every sync event, we check the token and the feature flag, we calculate the next state, and we go we fall back to the legacy state if something is wrong. So these are two further components that achieve redundancy. We can achieve some redundancy for our systems. All right, so far we talked about some redundant components in software engineering, how we use these redundant components to help us during migration or transition phases. And the last thing I'm going to talk about is adoption and cleanup. So I think the most important thing after you're done is that you don't leave all that complexity behind. You clean up your code once your migration is done. And that is actually pretty easy to achieve if you have done all the upfront work, especially with substitutable type hierarchies. And most probably you're working in a team, so I think it's very important you communicate with your team. You're doing this huge migration. You should also take ownership of the migration, which means that you have a lot of responsibilities. And it's actually your duty to be vigilant on PRs during these migration phases. So if something slips through the cracks, it's on you. And at Payback, we actually let people or project owners who are driving these huge migrations, we give them more leeway in being able to reject PRs. And we all know that we hate a lot of power and the power to reject PRs. All right, so let's look at cleanup. If we look at the initialized risk example, to clean things up, you just have to delete some classes, and that's it. So pretty easy. Same thing for the auth migration. All the complex state machine, you just, delete that, it goes away, there's no more complexity, and, well, that's it. Okay. Thanks a lot, and if you have any questions, I'll be happy to respond.